All right, we're looking at another integration technique, partial fractions. So basically, sometimes when you have a rational function that you're integrating, you can see right away that you can do a quick substitution that will work. But sometimes the factors don't work out. Okay, so this one's difficult to do that. In this case, we're going to express the function as a sum of two simpler irrational functions. If we can factor that original denominator, then we can split it up, okay? And basically be a sum of, could be more than just two rational functions. Depends on what the denominator is. So for example here, x plus 5 over x squared plus x minus 2. Factor that denominator. So that's going to be x plus 2, x minus 1. And then we know that we can show it as some expression over x plus 2 and some expression over x minus 1. Just thinking about back to basic fractions, right? Like if we have 1/3 plus 1/5, then our common denominator is going to be 15, right? 3 times 5. So here's your 3 times 5, these two brackets, and we split it up. We just have to figure out what that A and B value is in each. Okay, so now what we end up doing, so now we work with this to get it back to the beginning. So what's our common denominator? It's the original, so we would have to multiply top and bottom. Right here. So this by x minus 1, and this by x plus 2. Right? So here, this will be a times x minus 1, the other denominator, b times x plus 2, okay? And remember, when we solve rational equations, we end up multiplying through by the denominator, so the denominators go away. So basically this equals all of this, okay? Then from there, I'm going to switch back to blue. We know that ax minus a plus bx plus 2b equals x plus 5. So we want to group the terms that have x together. So ax plus bx equals 1x, right? Actually, I'm going to just group them first within this. So ax plus bx, then minus a plus 2b. Then you can see if you factor out an x, you have a plus b x. Here, the whole thing. So you could actually show this. Maybe I'll put the positive term first. So that's a plus. So that must mean that a plus b has to equal 1. And then if this is a plus here and this is a plus here, then this whole bracket has to equal 5. So then it's a system of equations. All right, now I might actually rearrange this because then I can add the equations. So I'm actually going to go, okay, I'm going to keep it as negative a plus 2b. Now when I add my equations, back to math 10, you get 3b equals 6, so b equals 2. Substitute that in. A equals negative 1. Okay, so therefore, now we can fill that in. So now we can split this up. A is negative 1, and that first denominator we said was x plus 2. And then b was 2 when the denominator was x minus 1. And then you can split that up. Okay, so you can split this up, right, and then just integrate each one. So here, the negative, and it's going to be ln of absolute of x plus 2, plus 2 ln of absolute of x minus 1, plus c. Okay? So the example above involves a rational function that can be expressed as a sum of two or more rational functions with denominators that are non-repeating linear binomials. Binomials, two terms. Linear degree 1. Okay, no squares, cubes, anything. Non-repeating, they were different functions, so they both weren't the same. Okay, so in general, when using the technique of partial fractions for integration, we will always express the rational function as a sum of simpler rational functions. Okay, so here's one. So take a look at the degree of the numerator and denominator. So degree of denominator, if it's greater than the degree of the numerator, and the denominator factors into 2 or more non-repeating, this is an example. So we're not going to write out the steps, we're going to do it. Okay, so x squared minus 5x, higher degree than the numerator. This factors, okay, and so basically, I guess you could do the factoring first, okay, to know that they're non-repeating. So now I do the work on the side. Don't do it all within the interval, right? So 3x minus 20 over x times x minus 5 equals something over each of the factors. Doesn't matter which one. Your neighbor might even use different letters, okay? It's a process. So now, that means if I multiply through by the common denominator, which is x times x minus 5, this denominator goes away, the x's go away, and we're left with a times x minus 5. Then the x minus 5 goes away, and we're left with b times x. Now you want to expand out the brackets. And group them. Okay, so that means a plus b has to equal 3, and negative 5a has to equal negative 20. So this one's pretty easy, because right away a is 4, therefore 4 plus b equals 3, so b equals negative 1. Okay, so then we go back in and show our integrals. We can split them up right away if you want. So that would be 4 over x. And then you can use the subtraction. That takes the negative out. And then that would be 1 over x minus 5 dx. Okay, so that's going to end up being 4 ln of x minus ln of, these are all absolute value, right, because we don't know what x is. And so we're done. Okay. These ones are fun. Okay, next one. So same, denominator is greater degree than numerator, but factors into 2 or more repeating linear binomials. So let's see. So if you need to do factoring work, do it on the side. So x cubed minus 2x squared plus x. So x is common. And then that factors to x minus 1 squared. So I'm going to show this. All right. Okay, so in this case, a little bit different. So we have our 2x squared plus 3. So I'm going to have a over x, just like before. Then we have to have b over x minus 1. And you might think, oh, I'm going to stop there, because those are the only 2 different factors. But we also have to have it over x minus 1 squared. And you might think, oh, well, that's degree 2. So I should put a degree 1 expression in the numerator. Nope. The actual factor there is degree 1, so we need a constant here. I'm just going to call it c. Okay? So 1 for each of the different factors, and 1 for the repeated together. Then if we multiply through by the lowest common denominator, which is that original denominator, then we would have here, x's divide out, we'd have a times x minus 1 squared, b times x times x minus 1 plus c times x. So what's that going to be? Ax squared minus 2ax plus a plus bx squared minus bx plus cx. All right, so now we might have three equations just because of the degree of this. So x squared terms, so 2 equals a plus b. X terms, 0, because there's no x term on the left there. Negative 2a minus b plus c. And constant term 3 equals a, and that's it. So that's nice. We know that a is 3. So then I would put that back in to the first one. So b is negative 1. Then I would put into the middle one. So c is 5. Okay. Then let's split it up. So this is going to be integral of a is 3. So 3 over x dx plus the integral b is negative 1. I'm going to keep it there for right now. And then c okay. So that's going to be 3 ln x. It's going to be minus ln of x minus 1. Okay, then here, if you need to do a substitution, it would be u equals x minus 1. So this would be 5, integral of 1 over u squared du. So that's going to be u to the negative 1 over negative, so minus 5 u to the negative 1, and then plus c. And then substitute back in. This will all be in terms of x's. U is x minus 1, so that would be 5 over x minus 1, c. Okay. Next example, degree of denominator greater, so same as the last one, but has an irreducible quadratic factor. So you can't get the quadratic factored into linear, okay, but factor what you can. Now you could here factor out a 3, you'd have x squared plus 5, but when you factor out a 2x here, it's not going to simplify, so I'm going to leave it, leave the numerator. 2x here, I've got x squared plus 3. Okay, so notice how I can't factor x squared plus 3. So what do we do in this case? Well, just like normal, I'm going to take, now in this case there is a denominator of 2. So rather than include that in everything, because it's going to be common to all of it, you might actually want to, I'm going to leave it out there, and then here, actually I'm just going to erase it from this. Oh, okay, let me do the whole thing. Sorry. So this would end up being, I'm going to keep the 2 factored out, so that would be 1/2. And then I'd have x times x squared plus 3. Okay. All right. So then it just eliminates some common factors too many times. So then I'm going to start with my linear factor x, so a over x. And then for my next factor, the difference here is this is not a linear factor. So that the numerator always has to be 1 degree less, okay? And then we have to incorporate coefficients. So I'm going to use b, x, and could have a constant term, Okay? It doesn't really matter what letters you use, but, and you could certainly switch them around, but you just have to substitute back in correctly. Now if I multiply through by the common denominator, then I'm going to get 3x squared plus 15 equals a times x squared plus 3, plus, then it would be x times bx plus c. So that would be ax squared plus 3a plus bx squared plus cx. So then my x squared, 3 equals a plus b. My x term, 0, equals c. And my constant term, 15, equals 3a. So right away I know c equals 0. Here I know a equals 5. And so then 3 equals 5 plus b. b equals negative 2. So now, I'm going to have a, which is 5. So that's going to be 5 over x. Okay, then plus 1/2. b is negative 2. So that's going to be negative 2x. c is 0, so just negative 2x over x squared plus 3 dx. I forgot the dx here. Okay, and so really that's going to be 5 over 2 ln of x. Notice here 2's divide out, and you can let u be x squared plus 3, so du would be 2x dx. So actually, I probably wouldn't divide out by that out. Anyway, maybe I will. Half du equals x dx. So, got a minus. Then the half, because there's the x dx, integral of 1 over u du. That's going to be ln of u, and then we substitute the back in. U, I said, was x squared plus 3. Now, if you didn't have absolute on x squared plus 3, you'd be fine, remember, because it is going to be a positive. Okay? And the last one. So here, the degree of the denominator is less than or equal to the degree of the numerator. Anytime you have that, split it up. Use synthetic or long division. In this case, we use long division, and split it up as much as you can. Okay, so long division, probably haven't done it for a while. 3x to the 4th. Leave a space if there's any missing terms. In this case, there isn't. Okay, so x squared goes into x to the 4th, x squared, and there's a 3. So I'm going to put that above the x squared. So those subtract, and then negative 5x squared plus 6x squared is x squared. Bring down the x and the minus 1. So plus 1. Subtract, and that's going to be positive 1. So this is the same as, remember it's your quotient, plus your remainder divided by the original divisor. Okay. So this is going to be 3, actually you can bring 3 out. All right. right, and then factor that denominator. That will be x plus 2 times x minus 1. And we did something similar. Oh, but it had a different numerator. Okay, so here, 1 over x plus 2 times x minus 1 equals a over x plus 2 plus b over x minus 1. So 1 equals a times x minus 1 plus b times x plus 2. So, x terms, 0 equals a plus b. Constant equals negative a plus 2b. We can just add those right away. Okay, so we get b equals 1/3. Okay, then we need to get a. So therefore 0 equals a plus 1/3. So that means a has to be negative 1/3. Go back up here. Okay, so now it's going to be 3x cubed over 3 plus x plus the integral. So a was negative 1/3 over x plus 2 plus positive 1/3 over x minus 1. So I like to, I know that's messy, so then I bring out the negative 1/3. Yeah, you could bring the 3 down and take the ln of that, etc. Well, no, because you still have to substitute in. But this is, I find, the cleanest way of doing it. And there you go. Okay, that's it.